We will deal shortly with what happens if we do have some sort of resistance force, but let's first think of what we still regard as an ideal oscillator with no friction, no drag forces, but we want to drive that oscillator with some force function. Now, one way to think of that is you got a kid on a swing. Kid swinging back and forth, and you're over here and you give the kid a push. So you give a push, a push, a push, a push, and you time that push so that it maximizes the motion of the swing. Now, the force you exert on a child on a swing, or a person on a swing, doesn't have to be a child. Adults like swings as well. That force is actually continuous, but it's more of an impulsive force. It more occurs just for a short time at a certain point in the swing. We could also be on top of the swing up here, pulling back and forth on the rope in a more continuous fashion. And that model might be a little better. It just is something to image, an image to kind of understand what's going on here for some sort of a continuous force function. Now, if we apply the force, if we're applying the force to a person on a swing, we're probably going to apply that force in a way that we time to be most effective. But if we set up some kind of mechanical driving force that isn't necessarily responsive to the motion of the system, then that applied force might resonate with the system and it might not. In other words, we could be pushing the person here at a different frequency than the pendulum wants to swing, or the swing wants to swing. The swing's actually a pendulum. And if we don't synchronize that force well with the system that we're trying to drive, then that applied force will sometimes reinforce the restoring force. Okay? And remember, the restoring force is a force that tends to move the pendulum back toward equilibrium. And if we apply a force that doesn't work well with that restoring force, it's not going to have the effect that we're after. So the applied force can reinforce our restoring force or it can oppose our restoring force. If we get out of sync in driving that swing or whatever system it is we're trying to drive, we're not going to be very effective, and we could actually end up messing up the oscillation quite badly. So that the applied force can reinforce our restoring force, it can oppose our restoring force, or can vary the degree of reinforcement and opposition as time passes. If we're applying some sort of a random force, we might apply it at a time when it works, and we might apply it at a time when it doesn't work, and as time passes, it sometimes might work, it sometimes might not work. So we're going to let F sub applied of t stand for whatever force it is we happen to be applying to the system. And our equation then is going to become my double prime equals negative ky. That's there. This is the net force, my double prime by Newton's second law, mass times acceleration. This is the restoring force, and that restoring force is always there. But now we're introducing an applied force, F applied of t, which I abbreviate down here by F app of t, so that our equation can be rewritten. Again, if omega naught equals the square root of k divided by m, we move this term over here, it becomes positive, and we get this equation, y double prime plus omega naught squared y equals F applied of t divided by the mass. Now, to put this in the context of things we've just seen, this is in some ways similar to the equation y double prime minus y equals cosine of t. Cosine of t would be a perfectly valid driving force, a nice periodic driving force for some periodic motion, which would hopefully have a frequency that matches the periodic motion. Now we have a plus here where we had a minus here. And you recall that this equation, the homogeneous equation, had a solution which was a combination of exponential functions. If this minus becomes a plus, our characteristic equation is going to have imaginary solutions, and we're going to have sines and cosines rather than exponentials. But other than that, this equation is very much of a form similar to those that we've been looking at, and the solution methods are going to be very similar. It could be that our applied force is such that we can use undetermined coefficients to solve the second order linear homogeneous equation. It could be that we might, in some cases, need to use variation of parameters to solve the non-homogeneous equation. However, the homogeneous equation is going to have a fundamental set y1, y2, which is simply e to the I omega naught t, e to the negative I omega naught t. Should be familiar at this point. And that would lead to a fundamental set. Actually, I've got an equal sign here, and that's not appropriate. Let's just say we could have another equivalent fundamental set, which is just going to be the sine of omega naught t, cosine of omega naught t. Again, you should by this point understand the connection between this and this. We use the Euler identity. This is going to be sine of omega naught t plus, or cosine of omega naught t plus I sine of omega naught t. And this will be the cosine minus I times the sine of omega naught t. That leads to the conclusion that this solution set works just as well as this solution set, where this one doesn't involve imaginary parts or imaginary numbers. The real and imaginary parts of the solutions we get from this set will each be solutions to the equation, and the solution will always have this form. You should recall all of that discussion. So our characteristic equation, in any case, using this fundamental set, is going to be C1 sine of omega naught t plus C2 cosine of omega naught t, which matches the solutions that we saw over here. And then the question just becomes, what's our particular solution? How do we find the particular solution? Again, depending on the nature of the applied force, our particular solution will be found by undetermined coefficients or variation of parameters, or perhaps by Laplace transforms, but that's down the road just a little while. We'll proceed in the next clip with some examples, or at least one example of this sort of a system. And then we'll move into some systems where we have not just y double prime and y terms in the equation, but where we also have y prime terms, and those y prime terms, as we'll see, will correspond typically to some sort of a drag coefficient, air resistance or frictional drag or something of that nature.